Next speaker is Valerii Tarhonskyi. Please, you have a word now.
Thank you. Hi, my name is Tarhonskyi Valerii, and today I will talk about the next job on convergence of homomorphism with inverse Poletsky inequality. This work was prepared by Dr. Evgeny Sebastianov and by myself. Let's start. Assume we have point x belonging D and mapping f from D to Rn. Then D belonging Rn is domain, equally that D is connected, an open set in Rn. We can see figure 1, a mapping of a domain D on this slide. Let's have the next definition. Length is a supremum, the length is a supremum of the length of polynomial lines of this form over all partitions of the interval AB by k points. And let's introduce the definition of admissible function for the family of curves gamma capital. Rho is admissible if it's Borel measurable and satisfies the condition second for all gamma small belonging gamma capital. On this slide, we can see the definition of the PEM modulus of gamma. And we can see also the visualization on the figure second. The model is real function of family of paths. Let's talk now about path joinings to set. Assume we have gamma capital for EFD. It is the family of all continuous curves gamma from segments 0, 1 to Rn, such that gamma in point 0 belonging the first set, gamma in point 1 belonging to the second set, and for all other t from 0 to 1, gamma t belonging D. We can see it on figure 3 as family of paths joining two fixed sets F and E. Let's recall the inverse Poletsky inequality. We have point x0 belonging D dashed, and x0 is not equal infinity. Let's introduce the following notation. B for x not R denotes the ball centered at point x naught and radius R. S for x0R denotes the sphere with radius R centered at point x naught. And also A for x naught R1, R2 denotes the ring centered at x0 and limited by R1 and R2. Let F be a mapping and let Q be a Lebesgue measurable function such that Qy equally 0 and let gamma indexed F for y naught R1, R2 denotes the family of all paths gamma from segment AB to D, such that F gamma belonging gamma capital for two spheres and ring. Other words, F for gamma A belonging the first sphere, F for gamma B belonging second sphere, and for all t between A and B, F for gamma t belonging ring for y naught R1, R2. We say that F satisfies the inverse Poletsky inequality and y naught belonging FD if the relation 5 holds for any R1 less than R2 less than R naught and any Lebesgue measurable function eta such that satisfies condition 6. We can see it on the figure 4 as the illustration of the action of a mapping with the inverse Poletsky inequality. On this slide, we can see some examples of mapping in the above inequality. In particular, quasi-regular mapping, it's the first one, and Sobolev class mappings with certain restriction on the dilatation. Let's talk about the theorem first. Let D be a domain in Rn, and let Fg be a sequence of cannot quasi-conform mapping. Cannot between 1 and infinity that converges to some mapping F locally uniformly in D by the metric H. Then F is either a homomorphism F or a constant C belonging at n dashed. So, what is about convergence of mapping for more general classes? For that, recall that the chordal distance between 2 points, x and y belonging Rn dashed, is defined via the projection of these points onto the Riemann sphere. We can see the explicit formulas that provided below this slide. Let's get next definition. If function as said has finite mean oscillation at a point x not belonging to dashed, if its integral deviation from the mean is finite. That is condition 9, where phi epsilon dashed is defined in 10. Also set q y not 0 r in condition 11, where omega n minus 1 denotes the area of the unit sphere as 1 s n minus 1 in Rn. And move on the main result of this work, the second theorem. Let D be domain in Rn n more or equal than 2, and let Fg be a sequence of homeomorphism that converge to some mapping F from D to Rn dashed, locally uniformly in D by the metric H, and satisfies the relations above 5 and 6 in each point y not belonging Rn dashed. Assume that one of two conditions holds, Q belonging FMO Rn dashed, or the second one, and then F is either a homomorphism F or a constant C belonging Rn dashed. This slide presents a result showing that the divergence of the integral above a pointwise condition. If the condition isn't satisfied, one can construct a corresponding sequence. This result is published in European Journal of Mathematics. It's over. Thank you very much.
Thank you very much, Valerii.